Hi and welcome. This video is the second part of a tutorial on events in C#. In this video, we'll create a practical example where multiple events exist in a class. We'll look at using add and remove accessors to encapsulate the functionality that gets executed when client code or calling code subscribes or unsubscribes to the relevant events. Code within the add accessor is executed when the client code subscribes to the relevant event. Code within the remove accessor is executed when the client code unsubscribes to the relevant event. We'll use the EventHandlerList built-in C# collection class to store the relevant delegates associated with the relevant events when the calling code subscribes. The EventHandlerList collection class is a built-in C# collection class that can be found in the system.component model namespace and is a collection specially suited for storing delegates. So here's the basic idea behind this code example. A device, could be any device, contains a thermostat which contains a heat sensor as well as a cooling mechanism. So we'll have a class to represent the device, a class to represent the heat sensor, and a class to represent the cooling mechanism. Each of these classes will implement an appropriate interface. So the heat sensor class will contain 3 events. One event that gets fired when the temperature of the device reaches or goes above 27 degrees Celsius, which is 80.6 degrees Fahrenheit. This event flags a warning alert. The cooling mechanism is switched on to cool the device back down to an acceptable temperature. We'll create another event that gets fired when the temperature of the device has reached or gone above 27 degrees Celsius and then subsequently falls below 27 degrees Celsius. This event flags an informational alert and the cooling mechanism is switched off. And lastly, we'll create an event that gets fired when the temperature reaches or goes above 75 degrees Celsius, which is 167 degrees Fahrenheit. This event flags an emergency alert. The device is shut down, and emergency services personnel are notified about the event. We discussed in the previous part of this tutorial that an event is raised either by the user's action, for example, the user clicks a button, or the code logic itself. In this example, we are going to use code logic to raise specific events. For more content on advanced C# concepts like this and much more, please consider subscribing and please ring the bell so that you'll be notified of future releases from this channel. Right, let's get started. Let's create a .NET Core console app and let's name this project and solution Thermostat Events app. Let's start by building a custom class to store our event information. Let's name this class Temperature Event Args. And let's make this class inherit from the C# built-in Event Args class. We want our custom class to store the current temperature, so this will be the temperature at the time when an event is raised. And we also want to store the date and time when the event was raised. So let's create an auto-implemented property named temperature and define it as the double data type. Let's create another auto-implemented property named currentDateTime and define it as the datetime data type. Next, let's create an interface named iHeatSensor. And we'll include definitions for 3 events in the iHeatSensor interface. All the events are associated with the built-in C# delegate named EventHandler. And here we can pass our custom class, the one we have just created named TemperatureEventArgs, that will be used to store event information, as a generic parameter to the EventHandler delegate. So let's create a definition for an event that will be fired when the temperature reaches or exceeds a predefined emergency level. Let's create a definition for an event that will be fired when the temperature reaches or exceeds a predefined warning level. And lastly, let's define an event that will be fired when the temperature has reached or exceeded the warning level and subsequently falls below the warning level. So next, let's create a heat sensor class to implement the iHeatSensor interface. And we want to explicitly implement the events defined in our iHeatSensor interface for the heat sensor class. So one way we can do this is hover our mouse pointers over the red squiggly line under the iHeatSensor text, then select Show Potential Fixes and then select Implement Interface explicitly. And now you can see Visual Studio has created our event implementations with add and remove accessors. Note that these add and remove accessors are very similar to the get and set accessors that are implemented for C# read-write properties. The add accessors will contain code that is fired when the client code subscribes to the relevant event. The remove accessors will contain code that is fired when a client unsubscribes to the relevant event. So we'll add code to the add and remove accessors in a bit. So one thing I forgot to do was include a method definition for running the heat sensor. Let's include the appropriate method definition in the iHeatSensor interface. And now you can see a red squiggly line under the iHeatSensor text in the class definition for the heat-sensor class. This is because we are not implementing all the members of the iHeatSensor interface. So to fix this, we can hover our mouse pointers over the red squiggly line, click Show Potential Fixes, and then click Implement Interface. And you can see that Visual Studio generates a method implementation for the method that we had not yet implemented for the iHeatSensor interface, the runHeatSensor method. We'll implement code for the runHeatSensor method a bit later. Let's create two member variables at the top of the heatSensor class, both defined as double. The first member variable is named warning level, and the second member variable is named emergency level. These member variables will store values that serve as our triggers for when a relevant event should be raised. For example, if the temperature of the device rises above the emergency level, the appropriate emergency event is raised. So let's set these values within a parameterized constructor. So let's create a member variable named _hasReached_warning_temperature, and this is defined as the Boolean data type. We'll see the significance of this member variable in a bit. Let's create another member variable which will reference a collection of delegates associated with the events implemented in this class. We could use any of the appropriate collection classes in C# for storing these delegate objects, but we are going to use the built-in C# EventHandlerList class for this purpose. So to use the EventHandlerList class like this, we must include a directive to the system.componentModel namespace at the top of our code. As mentioned earlier, the EventHandlerList class is a member of the system.componentModel namespace. Please navigate to this URL for more information on the EventHandlerList class. So let's create three static read-only objects, which will serve as key values that can be used to access the relevant delegates from within the EventHandlerList collection. Let's create another private member variable, which is an array of the double type, named _temperature_data. So this array will store mock data to simulate data coming from the heat sensor at regular time periods. So this data will be used to simulate the heat sensor outputting temperature data. So let's create a method named seedData and populate the _temperature_data array with data. Note that I'm deliberately including temperature data that is greater in value than 27, which will be used as our warning level. And toward the end, data that is greater in value than the emergency level, which will be set to a value of 75. This is so we can raise our events appropriately when the heat sensor outputs our mock values. Okay, so now let's implement the code for the add and remove accessors for the events that reside in the heat sensor class. So in the add accessors, all we want to do here is add the appropriate delegate to the event list handler collection, which is done at the point where the client code subscribes to the relevant event. So in the remove accessors, all we want to do is remove the appropriate delegate from the event list handler collection, and this is done at the point where the client code unsubscribes to the relevant event. You can see we are using the appropriate key objects when adding the relevant delegate to the collection. We are also able to use the appropriate key to remove the relevant delegate from our event list handler collection. So let's encapsulate functionality for raising the relevant events by creating 3 methods responsible for raising the relevant event for each of the events defined in the heat sensor class. Let's name the first method onTemperature reaches warning level. This method accepts one argument, which is our custom type named temperature event args. The temperature event args class is responsible for storing event data. Let's then write code to reference the relevant event using the _temperature reaches warning level key variable to reference the appropriate delegate within the _list event delegates object, which is derived from the EventHandlerList class. When assigning the value stored in the _list event delegates collection object to the handler variable, we must typecast the delegate to the appropriate delegate type, which is the event handler delegate that accepts the temperature event args type as a generic parameter. Then we need to see if indeed the client code has subscribed to the relevant event. If the client code has subscribed, then the handler variable will not be null. So if the handler variable is not null, we can raise the relevant event by executing the handler delegate object and passing in the appropriate arguments to the handler delegate. The this keyword is the first argument which references the current object, which of course is an object of the heat sensor type. The second argument contains relevant event information and is of the temperature event args custom type. If you'll recall, we made provisions for storing the current temperature as well as the date and time of when the relevant event occurred in the temperature event args class. Right, and we can now repeat the same basic pattern for the other 2 methods responsible for raising the other 2 events declared in the heat sensor class. So let's implement a method to encapsulate raising the temperature falls below warning level event handler event. And let's implement a method to encapsulate raising the temperature reaches emergency level event handler event. And now let's implement a private method named monitorTemperature. This method simulates the heat sensor outputting temperature information for the device being monitored. So this method traverses the data stored in the _temperature data array, which contains our mock temperature data. Let's write code to display the temperature to the console screen each time a temperature is read from the _temperature data array. Then we can create an else-if ladder whereby we can compare the temperature output to the warning level and the emergency level. The emergency level has the highest value that will be evaluated, so this is the first value that will be evaluated. If the temperature is above the emergency level, the emergency event is raised. Else, if the temperature is above the warning level, but below the emergency level, the warning event is raised. Else, if the temperature was above the warning level and subsequently falls below the warning level, we can raise the temperature falls below warning level event. Note how we are using the _has reached warning level Boolean member variable to evaluate if the temperature falls below warning level event should be raised. The _has reached warning level variable must be set to true when the warning level reached event is raised so that the temperature falls below warning level event can be raised when the temperature subsequently falls below the warning level. When the temperature subsequently falls below the warning level, we must set the _has reached warning level variable to false. And for effect, I'm going to introduce a 1-second delay between iterations of the _temperature data array. As you can see, I'm using the system.threading.thread.sleep method for this purpose. I'm passing 1000 as an argument to this method. This value denotes 1000 milliseconds, which is 1 second. And let's finish off the heat sensor class by implementing code for the run heat sensor method. So we'll simply write the text heat sensor is running to the screen to indicate that the heat sensor is running. And then let's call the monitor temperature method. Okay, so let's create the interface for the cooling mechanism class. Let's keep this really simple. So this interface contains two method definitions, one named on and the other named off. As the names imply, these methods represent the behaviors of switching the cooling mechanism on and off. Let's create a class named cooling mechanism and implement the iCooling mechanism interface. And each method will simply write appropriate text to the screen. Let's create an interface named iDevice. This interface contains two method definitions, one named runDevice, the other named handleEmergency. We'll create the class that implements the iDevice interface in a bit, but let's first create a class to represent the thermostat. Let's first create an interface named iThermostat. This interface contains one method definition named runThermostat. Right, let's create a class named thermostat that implements the runThermostat method. Let's create a member variable of type iCooling mechanism. Let's create a member variable of type iHeatSensor, and let's create a member variable of type iDevice. Let's create two constants, one to store the warning temperature level, which is set to 27 degrees Celsius, and one to store the emergency temperature level, which is set to 75 degrees Celsius. Please note that these figures are arbitrary and serve only to help us with the code example. Let's create a parameterized constructor that accepts an argument of the iCooling mechanism type, an argument of the iHeatSensor type, and the iDevice type. We want the thermostat to have a reference to the device to which it is attached. Let's set the appropriate member variables to their counterpart arguments within the constructor. Let's create a method where we'll wire up the events contained in the heat sensor class. Let's name this method wireUpEvents to event handlers. So let's use the heat sensor object passed into the thermostat class to wire up all of the appropriate events. So to do this, we can write _heatSensor dot the event name, which is in this case temperature reaches warning level event handler, then followed by the += operator. Then we are able to press the tab key to auto-generate an appropriate method definition. Then we can rename the method if we choose and click the Apply button to confirm the change. So let's write code to wire up the remaining events. So in the runThermostat method, let's add code to write that the thermostat is running. Let's call the wireUpEvents to event handler's private method. And lastly, let's call the runHeatSensor method on the _heatSensor object. Let's write code for each of the client event handlers. So to handle the event, for when the temperature reaches or exceeds the warning level, let's first change the color of the font to dark yellow. Let's write warning alert. The warning level is between warning level and emergency level to the console screen. Let's then write code to switch on the cooling mechanism. Then when the temperature subsequently falls below the warning level, we want the font to change to a blue color. And let's write information alert, temperature falls below warning level is between warning level and emergency level. And then to handle the emergency event, let's change the font to a red color. Let's output emergency alert, emergency level is emergency level and above. And this event is handled slightly differently to the other event handlers because we are calling the _device object's handleEmergency method. We are using the iDevice interface to handle the emergency event in the device object's code, which we'll soon implement. And we must make sure that each font color is reset after each event is handled. Okay, so now let's create a class to represent our device, i.e. the device that we are monitoring for temperature changes. Let's name it device and within the class's definition, let's indicate that we wish to implement the iDevice interface. Let's hover our mouse pointers over the red squiggly line under the iDevice text, click Show Potential Fixes, and then click Implement Interface. And Visual Studio auto-generates implementations for the members of the iDevice interface for us. So let's implement code for the handle emergency method. And we'll simply write out a basic narrative of what should happen in the event of an emergency. So let's write sending out notifications to emergency services personnel to the console screen. And then in the event of an emergency, we also want to shut down the device. So let's create a private method named shutDownDevice. And this method simply outputs a narrative stating that the device is shutting down. Let's call the shutDownDevice private method from the handle emergency method. Let's implement code for the runDevice method. So let's simply output that the device is running to the console screen. Then we want to construct our objects for our cooling mechanism, heat sensor, and thermostat components. And we'll use their interface abstractions to define each of their types. And I've encountered a bit of a snag here when writing the code to construct the heat sensor object. We have already created the constants for the warning level and emergency levels in the thermostat class. I think these constants should rather be members of the device class and passed into the heat sensor class during the construction of the heat sensor object. So let's create the two relevant constants in the device class. And so that we can encapsulate the values of these constants and expose the values of these constants publicly, let's create two corresponding read-only properties. Let's first create definitions for these read-only properties in the iDevice interface. And then let's implement the code for these properties in the device class. And then within the thermostat class, which has a reference to the relevant device object, we can replace the references to the relevant constants that once resided in the thermostat class with references to the relevant read-only properties of the device object. Okay, let's then write the code to run the device from our main method. So let's write code to prompt the user to press any key to run the device. Then let's instantiate an object for the device. Then let's call the relevant object's runDevice method. Sorry, I know I'm jumping around here a bit. We still need to finish off the code for the runDevice method. Let's finish creating the thermostat object. Then let's call the object's runThermostat method. Let's run the code. And you can see by the status output the device is running, the thermostat is running, and the heat sensor is running. The temperature changes of the device can be seen with the output of each temperature to the console screen. A warning event is raised when the temperature exceeds 27 degrees Celsius. The cooling mechanism is then switched on. But there's an issue because when the temperature subsequently falls below 27 degrees Celsius, the relevant status is not being outputted to the screen. Instead, the code is raising the warning event. So let's investigate what is going on here. And the issue was caused, I think, because of all the copying and pasting. I forgot to change the call to the onTemperatureReaches warning level method to a call to the onTemperatureFallsBelow warning level method. Obviously, a call to the onTemperatureReaches warning level method is inappropriate for the condition when the temperature has reached or is over the warning level and then subsequently falls below the warning level. So let's fix this issue and let's run the code. And that is a correct result. We can see the cooling mechanism is turned on when the temperature of the device exceeds the warning level. And when the temperature has been above the warning level and subsequently falls below the warning level, the correct event is raised. The correct status is therefore outputted to the screen in a blue font, and then the cooling mechanism is switched off. And we can see that all the events are firing correctly and being handled correctly. Toward the end, the emergency event is being handled correctly, which is in line with the market temperature data that we created for this example. Great! I hope you have enjoyed this video on handling multiple events within a class, using the add and remove accessors. We also used the EventHandlerList built-in C# collection class to add and remove the relevant delegates for when a user subscribes or unsubscribes to an event. Please consider subscribing for more content on advanced C# concepts and much more. And please ring the bell so that you'll be notified of future releases from this channel. If you feel you have gained value from viewing this video, please give this video a thumbs up. It will be greatly appreciated. Please feel free to share any of the videos created by this channel with anyone you feel may benefit from their content. As always, the code created in this tutorial can be downloaded from GitHub. A link to the relevant repository has been included below in the description. Thank you and take care.